There you go. All right. Okay. Facing the board the whole class?
Tomorrow you can afford I learned into one of them, and I could tell you when you turn around.
Well, I turn. Okay. I'll try to stay close. All right. So if we're going to talk graphs here, I'm talking every graph you've ever learned to draw, other than conic sections. Knowing these basic shapes helps you in anything you do mathematically if you know what the basic graph is going to look like. Okay, I am organizing these. The first column here is going to be everything that has x to the first power in it. Okay, and so we're going to start with the most basic graph of all, y equals x.
Okay.
What? Yes?
Yesterday, Mr. Phil tried telling
No,
me.
Okay, back on. Okay, y equals x. What is the graph of y equals x? Yeah, it's your basic diagonal line. Now, I know you don't probably need this information, but because I want you to recognize what it is, I'm going to tell you. Y equals x is saying, hey, when I put 0 in for x, I get 0 for y. 1 in for x, I get 1 for y. 2 in for x. And so I get, yes, your perfect diagonal line. And I like to think you all can graph that just fine. Okay, all lines that we graph are actually just alterations of that line. Transformations would be the technical term, except I didn't put that. Should be so do try to go through the corners of your boxes as you draw this. No, don't do that. Rat. Okay, there we go. So we get y equals x. Lovely line. If, well, we'll get to it here in a little bit, but what happens if I make it y equals 2x? How does the line change if it's 2x? It's the slope. We rise 2, run 1. So we know slope changes everything. Okay, what happens to this graph if I put plus 3 on the end of it? It goes up 3. Okay, when you guys were first taught lines, you were taught that, oh, that's the y-intercept. But we now know with our rules for shifting graphs that you put plus 3 on any graph, and it goes up 3, which makes the y-intercept 3. The whole thing jives. Okay. Then, last year we took and made a slight alteration of this graph, and we changed it into absolute value of x. Does anybody remember what changed because we put the absolute value? Yes, it becomes a v because of the fact that the negative side numbers still have to go positive. So the right-hand side of this graph is exactly the same, just your normal v, but the left-hand side, or a normal diagonal, sorry, but the left-hand side has to go upward because you're going to get positive values out of an absolute value. And then the funky one we learned that also is a form of a linear graph. Do you remember what the one in brackets with an X means? It is the stair steps. Does anybody remember the name of the graph? Great. Yes. And just to ring your bells a little bit about what on earth is greatest integer. Now I don't have a color to write with on here. This is proving to be a pain. Okay, so. Okay. Greatest integer, just to give you a reminder of why greatest integer does what it does, if you take and do a value and you put it in the greatest integer brackets, if I do the greatest integer of 1.1, it means it's going to take that back to the greatest integer value that's less than 1.1. What are the integers? Positive and negative whole numbers. So 1.1 would go back to 1. If I do 1.2, it goes back to 1. If I do 1.5, it goes back to 1. It always goes to the one lower than it. If I do 1.9999999, it goes back to 1. But the moment I get to 2, it's on 2. And then 2.1 is on 2. So when you graph this, you'll notice it stays on the same y-coordinate, and then all of a sudden it's going to hop to 2. And it's going to stay on that same y-coordinate, and it's going to hop, which is why we get the stair-step look. So, consequently then, if I want to draw this one, I need to go, it actually starts, the easiest place is you start at the origin, it stays on 0 until I get right over to 1, but at 1, it has to hop up and be 1. So when we get really, really close to 1, we put an open circle to say it goes as far over as it can, hops up. Goes over, hops up. So it literally, it stays on each value and then hops. And it functions as...
That's distracting.
Functions... Hush. We will have to contend with it. I can't think it's going to have to last that long, I hope.
That really smells, Tim. I don't know.
And the downside of this one is it's a pain to draw because it takes forever.
Oh yeah, these ones are terrible, aren't they?
Yeah. But same thing, because it's, if you actually look at the purple, the dark dots, the filled in dots, they're going through 0, 0, 1, 1, 2, 2, 3, 3. This is just the same as the diagonal line we did up above. So if I change the slope, it just changes the slope of the starting dot. If I put +3 on it, this starting dot will go up to 3 where it starts. The shifting and all that is still the same as it is with a regular line. It's just that you end up with a little wacky stair steps. Or somebody calls it the tadpole graph.
Tadpole. Let's look at tadpole.
It's not one we use tons, but okay, I've had people say, well, where in the real world would we care about a graph that does that? Yes. No. Oh. What, you give me an example where in the real world we do a graph like that? Okay. My classic example of step functions is volume pricing. If I buy from 1 to 10 calculators, I pay this price. Doesn't matter whether I buy 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm going to be at a certain level. But the moment I get to 11, maybe 11 to 20 calculators, the price actually drops. But I stay on that level to that point. Then I stay on that level. So lots of anything that's volume price like that, if you graph it, it's a step graph. Okay, that was everything linear, x to the first power. Now we're going to kick it up a notch, and we're going to move to x squared. Okay, so once again, if you don't remember the points you plot, you might want to write these t-tables down to help remember, but there's actually common sense. Anybody remember what numbers we typically plotted? 1, 1. Okay, you guys are giving me the y-coordinates. We normally plotted 0, 1, 2, 3 as x's, and then if you put them in there and square them, what numbers do you get when you square each of the? You get 1, 4, 9. So yes, you're remembering plotting many 1, 4, 9s. Okay, so if I plot that 0, 0, it's going to go different color here. 0, 0, 1, 1. Then I'm 2 over 4 up, 3 over 9 up. Okay. But what happens when I do the negative numbers? If you're going to square them, yeah, because negative 1 squared is still 1. Negative 2 squared is positive 4. Negative 3 squared is positive 9. So therefore we get our all-time favorite graph.
Parabola.
Yes.
Parabola.
We get the parabola.
Parabola.
Which we learned last year has multitudes of real-world uses. When we studied conic sections and we ran into parabolas again, we found out that parabolas are why our satellite dishes work and our headlights work. parabolas explain the motion of anything that you throw up into the air.
Yeah, it does.
So parabolas are pretty crucial.
Yep.
Now, obviously there's not another x squared graph I can do, but I can do its inverse and graph square root of x. Does anybody, how does it change these coordinates?
Well, obviously it makes them
Yeah, but these,
switches them around.
yeah, the x's and y's just switch. You put your 0, 1, 2, 3 over here on the right, and you've got your 1, 4, 9 over here on the left.
It's sideways, isn't it?
And so then, yes, it makes you have a sideways parabola. If we plot 0, 0, and then we go 1 over, 1 up, so this would now be 4 over, 2 up, 9 over, 3 up. And if you connect the dots, it looks like a parabola, but it's only 1/2. So should I put the other half of the parabola on?
I think you do.
No, because not on this one. Nope.
No.
Okay. First of all, would it be a function if I put the under one underneath it? No, it would not be a function. It would not pass the vertical line test. To get the bottom on it, this has to be plus or minus square root of x. So if that was plus or minus, then yes, you would have the bottom side under it. But in this
I
case,
told
no.
you that crack is whack, Miss Meyer.
Crack is whack.
So square roots are half parabolas. So now we'll kick it up one more. We're going to go to cubes. So if I want to do y equals x cubed,
Ah, you get it.
and then of course I'm also going to do cube root of x.
Hey, is this like what the extra credit was yesterday?
Yes, it's exactly what it was.
I failed.
Yeah, I kind of forgot how some of these graphs went in. I remember
Okay.
Nobody cares.
Anybody remember what shape x cubed was?
Parabola.
Okay.
Yeah.
Scrabola is what my students named this graph many, many years ago. Because it kind of looks like a squiggle, but they wanted the parabola sound, so they named it the Scrabola. Okay, but ever since we've named it, they never forget it. Before I could never get them to remember what x cubed looks like. Now we remember it's a Scrabola. So, if I'm going to do a Scrabola,
Jill and her fried friends don't count.
as far as the points you're going to plot, we're only going to do 0, 1, 2.
Jill and her five friends.
Back to the Scrabola.
Hey, he was talking about nobody cares about me. And
Okay, I'm recording. The people need to hear, so you all need to not be a pain. X cubed. We're cubing it. 0, 1, 2. If you're cubing your numbers, okay, 0 cubed is no problem. 1 cubed is 1. But what's 2 cubed? 8. Why am I not doing 3? It'll be 27, and I don't want to count 27 boxes. So, 3 cubed, 27. So when you plot it then, you're going to get 0, 0, 1, 1, and then all of a sudden 2 over is 8 up. You shot up quick.
What happened to the... Never mind.
Now on this one, what happens when I put negatives on those numbers?
It goes down.
It's when you cube a negative number, it will stay negative. So when you plot the negative side, you'll get -1, -1, and -2, -8. Which is why some people say it looks like a squiggle. Squiggle.
Say that again.
So if I come up, alright. So that's technically what we have named the Scrabola. Scrabola. Squiggle with actually it's got the S, they decided they wanted a U in it, sorry, I always forget that. It's S-Q-U. We had a big debate about how one would spell Scrabola. But if it's squiggle, it needs the S-Q-U. Scrabola.
there's always a U after a Q. Give me one word that does not
Now,
have a U after a Q.
does anybody remember what cube root looks like? Yes, it's a sideways parabola. Because once again, when you graph a root, all it does is it switches the x and y coordinates we had up here on the first one, which switching 0, 0, 1, 1 doesn't do much. But when you switch the 8 and the 2, it makes it go the other direction. So you will end up, since you're going over 8 and up 2, because anything cubed, when you, a negative number cubed is still negative. A negative number in a root is, in a cube root is still negative. I'm only giving you the starting values, and then you have to know what to do on the negative side. So this one's going to go, to me this is, this is the walk like an Egyptian graph. I see that old Egyptian looking. Oh, thank you. Good places to pause. Stop it then.